who's thank you, who's a machine learning engineer at NERSC. So works on running great things like this and supporting all of those who use NERSC for deep learning. But also is an expert in spatial temporal modeling, for example, for weather and climate applications, as well as in scaling laws for scientific machine learning and things like performance modeling, particularly at scale. So Shashank. And he's also our lead tutorial person for the supercomputing tutorial that we do regularly each year, which actually we're presenting kind of a modified version for this time, but we do also have all that material online as well if you're interested, which maybe you'll have links.
Thanks. Okay, yeah, thanks, Wahid, for the introduction. Okay, hopefully. Is that better? Yeah. Okay. Okay. So as Wahid said, this is going to be a slightly different talk where I'm going to be focusing on performance aspects of scaling deep learning models to large compute clusters, HPC machines, or data centers. So you heard on Tuesday that there's three main ingredients to building frontier models. One is your data. You want to make sure that you're collecting large data sets, preparing the data so it can be ingested by a deep learning model. The second is choosing an appropriate model architecture that gives you good performance or good accuracy as your model size increases or your data set size increases. Typically, transformer backbones are used here because empirically they've been shown to be extremely successful. And the last ingredient is lots and lots of compute. And that's what we're going to be focusing on today. So the goal here is to not throw a bunch of tools at you that you could use to scale your models, but rather the goal is to help you build some intuition on how performance works, how scaling deep learning models work, how parallelization of these models work. And the goal is to also show you how things work underneath the hood in some of these tools, and in general, what deep learning practitioners use at scale to get good performance. Okay, so hopefully the motivation is clear by now that training or pre-training large-scale deep learning models is super expensive. So this is like a graph that you can pull off the internet. It's from Epoch AI. There are a lot of cool graphs that show where the state of the world is in terms of building deep learning models. But as you can see, so the y-axis is training compute flops that some of these models use, and the x-axis is when these models came out. So some of these frontier models like GPT-4 or Google's models take more than 10 to the 25 compute flops to actually train. What does that mean? So this is the same graph, but different axis, where on the y-axis is how much time they use to train these models. And x-axis is once again the same thing, training compute flops. The takeaway here is that these models were trained on several weeks. So this is in days, sometimes even like several months, using thousands of GPUs or TPUs if you're building models in Google. So high performance computing resources are necessary to train these models at scale. And distributed training with performance optimization is key to getting good performance and to making sure that you're utilizing your compute budget effectively and efficiently. And this typically is done in a few stages. The first stage is more on the research side that you've already heard about, where you want to pick an appropriate neural network architecture and a data set that you choose as a researcher to work on your problem. And then you're satisfied that the model is able to give you some good enough accuracy, and now you're interested in scaling it up. But before you scale it up, you want to make sure that you optimize your model to work well on a single GPU. So you want to make sure that your data pipelines are feeding data fast enough to the GPU, so your CPU is not bottlenecking you. And in general, you want to make sure that you're making effective use of the GPU itself. Once you're satisfied with your performance on a single GPU, that's when you would think about scaling up to multiple GPUs. So people do this in different ways. The most common way is called data parallelism. That's when you split up your data set into multiple GPUs and scale. But for the larger models, this is insufficient. For example, if you're building a model with hundreds of billions of parameters, then the model itself, just the weights of the model take hundreds of gigabytes of memory, which no GPU has today. So you would have to scale up using additional GPUs using model parallelism. That means you're also splitting up your model across multiple GPUs. And you want to also make sure that you're using optimized libraries for getting performance at scale. So today in this talk and in the hands-on section that's going to follow, hopefully I can show you how you would scale a vision transformer for a scientific task. In this case, it's weather forecasting. So you already heard about both. You heard about the vision transformer and the transformer architecture, as well as the weather forecasting problem. And the goal is to understand how to optimize that model on a single GPU, scale up to a large dataset volume using data parallelism on multiple GPUs. And then we're actually going to see what happens if you make the model itself really big, such that it doesn't fit on a GPU, and then you would have to use model parallelism. And then if time permits, specifically for scientific problems like high resolution forecasting or things like imaging, like in medical imaging, your data resolution itself is really high, and you would have to use other flavors of model parallelism to actually scale your model. So this is kind of designed so that I'm going to be talking about all the methods in this talk, and then there'll be like a one-to-one correspondence to the hands-on section where you would do all of these different stages. Oh, I forgot to mention that the weather forecasting is just you're trying to predict the atmospheric state, and you want to emulate that process using like a neural network. We'll be using NERSC. I think some of you have already taken the NERSC tours, so you must know what it is. So we have a high HPC system here in Berkeley Lab. This is the DOE's Mission Science Computing Facility. And the system is called Perlmutter. It's a pretty large machine with 7,000 NVIDIA A100 GPUs, 128 petabytes of community file system, so people can share data, and 35 petabytes of Lustre, which is which is for fast I/O performance that deep learning models typically use. NERSC has a broad scientific user base, as Deep mentioned yesterday. We have like 11,000 users and thousands of projects. Okay, so just to set some context around the scientific applications, so you know what you're looking at, especially in the hands-on. The goal of weather forecasting is to model atmospheric physics. So you want to model atmospheric physics over the entire Earth. This is a very complicated phenomenon. It has processes that occur across many different spatial and temporal scales. Traditional models are partial differential equations with closure models to actually solve them numerically. And there can be hundreds of differential equations for weather forecasting because of all the processes involved. And they're regularly assimilated with observations. Like you have a lot of observational data that comes from like satellites and sensors globally. And every few hours, the numerical solver is assimilated with the observations through solving like Bayesian inverse problems. Numerical weather predictions extremely expensive. There's dedicated machines, compute clusters in different weather forecasting agencies around the world that's running 24/7. Today, there's a lot of interest in using neural networks because they can function as surrogate models. Essentially, they can learn to emulate the entire process. It's still very expensive to train these models, but you amortize that cost and influence because the evaluation is super quick. So when these models are actually put in production, they can be like thousands of times faster than a numerical weather prediction model. Today, these models are already in production. So ECMWF, which is the European Center for Weather Forecasting, already has its own AI models that's running in production in tandem with the numerical weather prediction models. So AI models have grown rapidly over the last few years. This slide does not do justice to the number of models that are out there, but just to point out, there's a lot of industry-driven models as well. So ForecastNet was on 2022 from NVIDIA. GraphCast is from Google that Danielle was talking about yesterday as well. And all these models are trained on very similar objectives. The weather forecasting objective is very simple. You're given the atmospheric state at time t. You want a neural network to learn to predict that state at time t plus delta t. All these models are trained on the LF5 dataset. LF5 is a public dataset that ECMWF, which is the European Weather Forecasting Center, maintains. It's a very rich dataset. It has 40 years of weather data on a 25-kilometer grid. You can think of that entire dataset as a tensor of size t cross v cross 720 cross 1440, where t is 40 years of data at an hourly resolution. So that roughly translates to like 300,000 samples. V is the number of atmospheric variables like temperature, velocities, humidity, water vapor, and things like that. And LFI has hundreds of variables. And 720 by 1440 is the spatial resolution of this dataset. It's often thought to be the best available estimate of the Earth's atmospheric state historically, and this is why it's used very commonly to train large deep learning models. So once again, the weather forecasting problem is given your state, which is a V class 720 class 1440 image. At time t, you want to predict the state at time t plus delta t. So these are just like snapshots of 3 different variables, like temperatures and velocities, to show you how it looks like. Okay, some more 101 on the transformer architecture, but specifically in the context of weather forecasting. You already know what a transformer is. Very simple. It's just self-attentions and MLPs repeated many, many times. MLPs are also known as feed-forward networks. The whole idea of a transformer is that it takes a sequence of tokens in and learns to predict the sequence of tokens out. So in all your language models, those sequence of tokens are like sequence of words. Like this is like for GPT-3, we'll learn to predict the next token, and it keeps doing that auto-regressively until it's finished generating your response. In weather forecasting, you would just replace that with your atmospheric state. So the architecture is unchanged, but your inputs and outputs now represent something different. It is your atmospheric variables at a specific time, and the transformer learns to predict those atmospheric variables at the next time step. And very similar to language, this is auto-regressively fed back into the transformer to get weather at, at let's say 6 hours, 12 hours, 24 hours, and so on and so forth until you hit like the predictability limit of predicting weather. Idea of vision transformers. You saw it yesterday, the sequence of tokens is generated by creating patches over the image and then feeding that into the transformer. So for weather, that looks like you had your input tensor of V different variables. You patch it up using patch size. Typically, people assume a square patch size, so it's P squared. So this is like a simple reshaping operation. And at the end, you have a sequence of L different patches. And this is projected onto a high dimensional space. E is called the embedding dimension of that high dimensional space, and that's where all your learning happens. Okay, so the common terminology here, very similar to language, is L is sequence length, and E is your embedding dimension. Okay, any questions on that? I'm just restating things that you've already heard about, but just in the weather forecasting problem. Okay. To parallelize deep learning models, it's good to have some mental framework which can help you understand how parallelization works, and then you can just use it for any type of model, any type of data, and actually scale it. And it's pretty simple. It's that you want to think of your neural network as a sequence of weights and activations. So every neural network is just multidimensional tensors that typically have weight matrices. These are your parameters that parameterize your models. These matrices are the ones that you're trying to learn, and that's colored in orange. And activation maps are from your data, or they're intermediate activations from like neural network outputs. So typical tensor dimensions are B is your batch size, L is your sequence length for transformers, E is your embedding, and weight matrices can be, say, 2D, or it can also be 3D matrices, depending on your input dimension. So you as a user, if you want to parallelize this model, is you decide which of these tensor dimensions are you going to split up across multiple GPUs. So the parallelization formulation is simple. I give you n number of GPUs, and you can decide how do I want to split things up so that I can use those n GPUs most effectively, and that's it. So if you decide that you're going to shard B, it's called data parallelism. That means you decided to split your batch dimension into multiple GPUs. If you decide that you're going to shard M or N, then that's typically called tensor parallelism. If you decide that you're going to shard L, that's called context parallelism. In language modeling, in science, it's also known as domain parallelism or spatial parallelism. And that comes from like numerical methods where domain decomposition is a very common way to split your work up. And if you decide to parallelize in the depth dimension, which is the repeating dimension, then that's called pipeline parallelism. Okay, so in this talk, I'm going to be focusing on data, tensor, and context parallelism because for two reasons. One is that pipeline parallelism typically doesn't help you too much, especially in scientific tasks. It's very useful in language models when your weights are really big, but in science, what usually happens is your weight matrices are not that big. You don't really have trillions of parameters, but your input activations are very big because they come from high resolution inputs, like in weather forecasting, or if you're doing things like medical imaging, these are like 3D images, which are very, very high resolution. So pipeline parallelism there will actually not help you reduce the memory too much unless you're very careful about how you choose it. And the second reason is that it is kind of difficult to get performance at scale with pipelining because pipelining is more of a scheduling problem. And if some things go out of sync, then you might see a performance drop at very large scales. So we'll be doing data parallelism, tensor, and context parallelism, and then we will do all of this in the hands-on as well. Yep, sorry. Okay, so using that mental framework, you can now reimagine your vision transformer. It's literally just taking those activation maps. So activation is colored in blue, weights are in orange. Once again, you're trying to learn weights. That goes to self-attention. The output of a self-attention is once again another activation map. Again, it's the same size, goes to MLP, and once again, the output is again the same size. This is why transformers are super nice. There's no like downsampling or upsampling, and things are usually very nicely load balanced. It makes a very attractive architecture choice because it has the least inductive bias. So what does the MLP do? You've already seen the neuron diagrams where it projects to a high dimensional space and comes back down. You can think of that as matrix multiplies or tensor shape with your tensor shapes. So you had an activation, which comes from the previous layer. That's of size batch, sequence length times embedding. So I've dropped the batch in the diagrams just for simplicity, but you can think of this dimension as B times L. So you have a batch of activations. It gets multiplied by a weight matrix. Typically, F is larger than E because you want to project to a high dimensional space. You get an activation, L cross F. There's a nonlinearity, which is a pointwise operation that you apply. And then you multiply by F cross E, which is a taller matrix to bring it back to its original dimension, L cross E. So your entire MLP operation underneath the hood, this is what's getting implemented on your GPU. It's just matrix multiplies with activation maps and weight matrices. You can do the exact same thing for self-attention. I'm going to skip this slide because you've probably seen it too many times now. But the idea is that you projected to queries, keys, and values, did some cosine similarity, and projected back. You can think of that same thing using matrix multiplies. You had an input tensor, same size as before. It gets multiplied by a weight matrix. It looks very similar to the MLP, except the dimensions are slightly different. I'm not going to go into the details, but you can look into the slides and convince yourself that this is pretty similar. In attention, you have things like number of heads because you do multi-head attention and the head dimension in order to do multi-head attention, but that's just like choosing dimensionality. And once you project to queries, keys, and values, and the reason we have 3 here is because there's 3 tensors, and usually that projection is done in one shot using a single matrix. You can do the attention operation, which is just computing cosine similarities, and then project back to your embedding space again, and the result is once again batch times sequence length times embedding dimension tensor. A couple of things I want to note here is that note that the attention operation itself has no weight matrices. There is no orange matrix here in the attention operation. That's actually one of the things that makes attention very attractive. All of these relationships is learned directly from data, and you can scale it however you want. But the second thing is that it also makes the attention a very expensive operation. So here L is your sequence length. In order to multiply these two matrices, this is the QK transpose dot product attention. The complexity of this scales as L squared, so it's quadratic in L. And also note that this matrix that you have to build is an L by L matrix times the number of heads times the batch, and that can be huge depending on how big your L is. So if you're not careful, you can really kill your memory and you can kill your compute if you don't deal with this properly. Okay. So given that mental framework and converting your entire vision transformer into tensor shapes, let's go ahead and data parallelize the transformer. Data parallelization is the easiest parallelization that you can use. I know most users already use them. But the idea is that if you understand how to do data parallelism, you directly understand how to do model parallelism as well. Okay, so what is data parallelization? The first thing you have to think about when you're parallelizing is that you have to think about both your forward and your backward pass. Typically, people forget about the backward pass, but your backward pass is usually twice as expensive as your forward pass. And the reason why you're utilizing a lot of activation memory is actually because you need it for your backward pass. So your forward pass typically looks like this. It's a matrix multiply again, nothing new. So if you have y equals x times w, your output tensor here is gotten by multiplying your input activation with a weight matrix. All good. What does your backward pass look like? This is backpropagation 101, which most of you know already, but I've just rewritten it in terms of matrix multiplies. So your gradient with respect to x is essentially gradient with respect to y, and that's the gradient of the loss with respect to y times W transpose using chain rule. So you can once again think of that as matrix multiplies. So grad y times W transpose, which is the transpose of this matrix, is equal to the grad x. And then you have the backward pass, which computes the gradient of the weights. That's basically x transpose times gradient of y. So if you transpose the x matrix, it's E times BL times gradient of y is BL times F. And you get gradient with respect to the weights, which is once again E cross F matrix. So it's this matrix that you will use in your optimizer step to actually update your weights and move your neural network closer to a local minimum. Note that the backward pass needs the X matrix. And in all automatic differentiation frameworks, like for example, what PyTorch will do is when it's computing the forward pass, it'll cache this X matrix in memory so that it can use it in the backward pass. And if you keep doing this in every single layer, that memory pressure can build if you're not careful. Okay, so in data parallelization, you as a user have decided that you're going to split the batch dimension into multiple GPUs. So let's assume you had two GPUs here. I'm going to split the batch dimension by 2. So GPU 0 gets the first shard, and GPU 1 gets the second shard. Note that both these GPUs will multiply by E cross F, which is the same weight matrix. So in data parallelism, your model is always copied on all the GPUs, which is a little bit of a redundant memory, but this is how it works. And then you can multiply these two matrices to get your final answer. And as far as the forward pass is done, you're actually done data parallelizing your transformer, because in order to multiply these two matrices, all the information that you need is completely local. So you need to take dot products of the rows of this matrix with columns of this matrix, and everything is present locally. So your final answer is already correct. And as long as if your data loader deals with splitting your batches up, your forward pass is automatically parallelized. So what have you achieved by parallelizing this? You have reduced your compute by 2 because your batch is split into 2 different GPUs. And in terms of activations, you've reduced the memory also by 2. But in terms of weight memory, you've done nothing. You've actually copied the weights on all the GPUs. So that memory pressure still exists. What about the backward pass? So when you backpropagate activation gradients, so when you do grad x equals grad y times W transpose, you can do a similar matrix multiply with BL by 2 times F multiplied by the transpose of your weight matrix to get the answer. And once again, your backward pass is also trivially parallelized. You have all the information that you need on your local GPU. But if you come to gradients of the weights, that's looking something like X transpose times gradient of Y. So once again, PyTorch will do this automatically for you, but what it will compute is transpose of the X matrix, which looks like E cross BL by 2 times gradient with respect to Y, which is BL by 2 times F, to give you an E cross F matrix. So it's the correct dimensions, but the final answer is only a partial sum. So normally you would have wanted to do a dot product of this entire row with this entire column, but every GPU only has a local shard. So at the end of the day, you haven't computed the correct answer. You only computed partial sums. Every GPU has computed a separate partial sum. So you're going to need some sort of communication between the GPUs to sync your answer. In this case, that's an all reduce operation. That's a collective communication routine that you can call using a distributed communication library. Where it'll basically sync the gradients by summing up the local gradient tensors across all the GPUs. General rule of thumb, if your inner dimension is sharded in matrix multiplies, then you need some sort of sync. So in this case, your inner dimension is BL by 2, and that's always split across multiple GPUs, and hence you're going to need some sort of communication sync. In the previous case, the inner dimensions are not split across multiple GPUs, so you're actually good to go, and you don't have to really do anything. One of the other good things about data parallelism is that there's a lot of opportunities to overlap that communication with computation. So if you think about it, the only communication that you're going to need is communicating the partial sums across GPUs using the all-reduce for the weight gradients. But the weight gradients you really need at the end for your optimizer step when you're actually updating your weights. So when you're actually doing your backward pass, you can keep doing the backward pass and communicating simultaneously. So how does that work? So in the forward pass, you would move from the input to the loss function by going through multiple layers of the transformer. And in the backward pass, you would start backpropagating your gradients from the loss. So you would compute the activation gradients and the weight gradients, and then you would fire off an all reduce for the weight gradients. And then you would just move on with your backward pass and start computing the backward pass for the previous layers. All of this, all reduced communications can be overlapped with this backward pass computations. And depending upon your model and your data size, you could hide a big part of your communication costs behind your compute. This is like a second reason why data parallelism is very attractive, because as you keep using more and more GPUs, while you do have to pay some communication costs, many times it can be overlapped a lot and you will see a good scalability. Okay, so once you're done with this, you're actually finished with data parallelization. One important thing to think about is from the optimization perspective. So when you're doing data parallelization, you want to use larger and larger batch sizes so that you can use more GPUs to actually make your training go faster. Since you're doing stochastic gradient descent, larger batch sizes will give you a more precise gradient estimate because you're using more samples to compute your gradient. And hence you can afford larger learning rates to move through your loss landscape. In practice, people recommend that you use like square root to linear scaling of your learning rates. So let's say if you made your batch size 4 times, you can either double your learning rate or do something between doubling your learning rate or 4 times your learning rate. You can't do this indefinitely. Data parallelism will stop for you at some point, and that is more of an optimization problem because large batch sizes may generalize worse. So this is like a paper that came out pretty long back, I think like in 2017 or 2018, where they showed that if your batch size is really big, then your optimizer would force your weights to converge to a sharp minimum. So in neural network training, your loss landscape is super non-convex. It's very jagged with a lot of sharp minima. And if you have more precise gradient estimates and less noise in your optimization procedure, then you might end up converging to a sharp minimum. And the reason why a sharp minimum is bad is because in this graph, the black curve is a training function, and the red one is your testing loss on, like, let's say, an out of distribution data set. And if the distribution is slightly shifted, then even though you're at a minimum for your training loss, for your testing loss, you're at a very high point. So your model hasn't generalized well. Whereas if your batch size is smaller, then you can actually take advantage of more stochasticity and actually converge to a nicer minimum, which is more flat, and that tends to generalize better. So there are trade-offs here to think about. So you don't want to increase batch size too much. in case you get worse performance in generalization and you have to throw out your network. While large language models can afford very big batch sizes, so they go up to like 2,000 or 4,000, in science, we don't usually see such large batch sizes because the model doesn't perform that well. Typically, people end up with like 256 or 512, and it stops there. So at some point, you can't scale with data parallelism purely. Okay, so that was how it works. In terms of the code, it's very simple. If you're using PyTorch, it's just 4 changes that you have to make to your code. You have to initialize the PyTorch distributed library using torch.distributed.init process group. That works very similar to MPI if you're familiar with MPI. So you basically tell Torch that you have X number of GPUs and initialize your communicator group. After you define your model, you would simply wrap it up in distributed data parallel, which is a library from PyTorch, and tell DDP, which is distributed data parallel, what the local rank of your GPU is. So what is your GPU ID that you're looking at? Your data set will split your batches, and for that, you just call distributed sampler, and that'll split it up for you into multiple GPUs. And when you actually run your code, you want to make sure that you launch one process per GPU so that processes are not contending for resources. And that's it. So these are the 4 steps. And once you have this, you can just start using more and more GPUs, and you can scale your training using data parallelism. How does it work underneath the hood? DDP takes care of everything for you. So when you call loss.backward to compute gradients, what DDP will do is it'll register an autograd hook to all your parameter gradients. And as soon as your gradient computation is done, automatically underneath the hood, DDP will trigger off this all reduce to sync your gradients. And all these things are overlapped with computation. There's a bit of a user-defined parameter here that's called buckets for DDP. So sometimes it's a good idea to pack your gradients in larger buckets, because if you have layers that don't have too many parameters, you don't want to keep firing off all reduces. There's a lot of latency involved in that. And like, for example, like layer norms don't have that many weights. So it's a good idea to keep packing your gradients until you hit some bucket size and then fire off that sync as and when the bucket is ready. This is a bit of a hyperparameter that you can tune. The default for bucket size is like 25 megabytes in DDP, but as a user, you can like switch it up or switch it down to see how it affects your overall training time. So you don't want your bucket to be too big, otherwise your overlap opportunities are lost. If your bucket is too small, you might spend time just in latency of communication. So once again, there's like trade-offs here to think about. For NVIDIA GPUs, you want to make sure you're using Nickel, which is the NVIDIA Collective Communications Library, which is very similar to MPI for optimized communication performance on GPUs. So Nickel underneath the hood will implement the all-reduce operation for you. And as I said before, data parallelism is the easiest parallelism to expose and most common. Most deep learning models can get away with data parallelism, and unless you're working with large models or large dataset sizes, it is generally not recommended to go towards advanced parallelization strategies. Okay. So now that you know how data parallelism works, model parallelism is very similar. Are there any questions on data parallelism? Yeah. Yeah, so if your model doesn't fit on a GPU, then you go to model parallelism. Yeah, if your models fit on a GPU, you're better off paying that redundant memory cost of copying models in every GPU. Technically, you don't have to do that. Like, you're wasting memory because the model is copied. But because there's a lot of overlap opportunities in the communication, we generally recommend that you just do data parallelism and get away with it. Also, from the code point of view, data parallelism is super simple. Most people already use it, and that's why it's recommended. But at some point, your model will overflow the GPU. And at that point, you have to think about sharding the model itself. And that's when you would use additional GPUs on top of data parallelism to actually manage your memory costs. Oh, yeah. So you can compute. So let's say I had 200 billion parameters, right? If I stored that in FP32, that's like 200 times 4 times okay, so a billion is 1 × 10⁹, and if it's as in gigabytes, it's like 800 gigabytes. So that's definitely not going to fit in your GPU. If it's 20 billion, it's 80 gigabytes. So that's probably going to fit on your GPU, but there's a lot other things you have to store. Like it's not just your weight matrix. You have to store your weights, your gradients, which is the same size as your weights. And depending on the optimizer you use, they keep copies of the weights and things like momentum if you're using Atom Optimizer. So there's like a scaling factor there. Usually it's like 6 times to 9 times the weight matrix. So if you think that your weight matrix is using, let's say, 10 gigabytes, you'll probably need like 60 gigabytes of memory. And if your GPU does not have 60 gigabytes of HBM, then it's going to overflow. But as I said before, it's not just your weights that's important. So you have weight matrices that you're storing, of course, but all those blue matrices there, those are intermediate activations. They also take up memory. So depending on the size of your model versus your activation, one of them can push you out of memory faster than the others, and that's completely dependent upon your problem choice and your architecture choice. But as long as you are thinking about it as just matrices that you have to store, then you can do a back of the envelope calculation and figure out how much memory needs to be used. Good thing is in the hands-on, there are like libraries you can use, which will summarize the model for you. It'll show you what the tensor shapes are involved in every single operation and every single layer. And it'll give you a rough estimate of how much memory is being used by the parameters, how much memory is being used for the forward pass, and how much memory is probably going to be used for the backward pass because you're like storing those intermediate activations. And that'll give you like a rough idea. Okay, it's going to take this much memory, so it's not going to fit. And I'm going to have to think about doing other things. Right. Yeah. That's right. Yeah, for data parallelism. You as a user have to make sure that your data loader is sending the batch shards to the different GPUs, but that's also just a call to a distributed sampler. So essentially, when you define your data loader, you would define a sampler called distributed sampler. And I'll show you exactly how that works in the hands-on, but it's just this function call. Distributed sampler just needs to know how many GPUs you have, and then it'll take care of splitting the batches up underneath the hood. You pass that to your data loader, and when you're just asking for samples from the data loader, it'll automatically only give you the local shard. And DDP will make sure that it does all the communications. You have to do nothing, basically. Right. So this is why this is super popular. It's got nothing to do with the complexity of the matrix multiplies. It's very easy from the software perspective, and PyTorch has spent a lot of time in analyzing how to create bucket sizes to overlap communication so that you as a user don't have to do much. In fact, I'll also go to say that in model parallelism, PyTorch is slowly catching up so that they want to have the user experience to be very similar. But I'll talk about that in the next few slides. Yeah. Usually for deep learning, it's okay. It depends on your model, but usually when you're building large models, you're using transformer architectures only because from an accuracy point of view, they scale better with model size and dataset size. The transformer is very nicely load balanced. It's just the same matrix multiplies repeated like 50 times. So the entire graph is static, which is why even in practice, and we will see this in the hands-on as well, people recommend that at scale, you just use like CUDA graphs and record the entire graph. And it's just like a single kernel call at the beginning. CUDA knows exactly what operations to run, and it's never going to be like rebalanced. The bigger challenge with transformers is that if your model becomes really big, there's multiple parallelization dimensions. And the trade-offs, so no single parallelization dimension will give you everything that you want. And then you have to play a little bit of a game to balance the different parallelization strategies, to balance either communication costs or memory costs. And that's a little bit of an art. You can build performance models to tell you how it works, but yeah, that takes a little bit of work generally. Yeah. Yeah. Right. Oh, yeah. So the question was, how do we determine which GPU processes which part of your batch, right? in this setting, you think of everything from the distributed memory perspective. That's your parallel programming model choice, which means all you have to think about is what a local GPU is doing, and it processes a random batch. So batches are shuffled randomly, and some random shard goes to some GPU, and every GPU gets a random shard, and that's it. You don't have to control which one needs to go to which GPU. So, for example, let's say I had 128 batches, and let's say I wanted to use 64 GPUs. Every GPU will get 2 batches randomly. The distributed sampler will randomly shuffle and then split up your batches in buckets of 2, and then it'll give it to every single GPU. And that's about it. Yeah. Yeah. Yes, it handles everything. So all reduce underneath the hood is handled by Nickel, which is like MPI, but it's NVIDIA's communication library. That'll handle everything for you. The reason why we recommend Nickel is because if your system has multiple bandwidths, like in Perlmutter, we have fast bandwidth domains and slow bandwidth across nodes. Nickel can do smart things to amortize the bandwidth between the nodes using the GPUs that's actually on the single node. Everything is taken care of for you automatically. So you could run it on 4 GPUs or 4 nodes or 100 nodes, and the already algorithm will work. Yeah. 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 Oh, right. So taking the average just means that you would take the sum and divide by the number of processes involved. In this case, in data parallelism, what actually happens is you're taking an average operation, even though it's still a call to all reduce, but you can tell all reduce to average or to sum or to do max or min. So it's all the same algorithm underneath the hood. The reason why it's an average operation is because your loss function is typically a mean squared error loss, which means you're taking an average over batches. But if your loss was different, let's say you're doing a sum loss, then you have to multiply by the number of processes. The PyTorch docs actually tells you this. Like if you go through the documentation, I'll put up all the resources in the end to be careful about this. But in general, I've seen deep learning folks use mean squared error loss, so you can just work on it. But yeah, but for average, you just sum everything up and then divide by number of processes. Yeah. That's right. Yeah. That's right. Yeah. Yeah. You don't touch the nickel stack unless you're a very deep performance engineer. Um, Everything is done on the torch level. That's right. Yeah. Okay. Okay, coming to the more exciting stuff, model parallelizing the transformer. This is what people do to train frontier models because your models are too big. The good news is if you understood how data parallelism works, model parallelism is the same thing. It's just like a different word used. So let's go back to the MLP. Remember, there's just a bunch of matrix multiplies. But in model parallelism, you as a user have figured out that your weights are really big because you want to train like a 100 billion parameter model. So these E-class F matrices are now becoming bigger and bigger and bigger because there's more parameters. So you decide to use more GPUs just to split this weight matrix up into multiple, into those GPUs. Okay. How does that work? Let's assume I use 4 GPUs to split up your weight matrix. So GPU 0 gets a shard of the weight matrix here. GPU 1 gets the second shard, GPU 2 the third, and so on and so forth. So you've reduced your memory pressure by 4 because you used 4 extra GPUs just to store this weight matrix. And now you can do your matrix multiply just like in data parallelism. Remember the rule of thumb, if your inner dimension is sharded, you need a sink. If it's not, you're good to go. So in this case, this is the first matrix multiply in the MLP. You're multiplying this matrix with this weight matrix. Your inner dimension E is not split across multiple GPUs. So you're already done model parallelizing your first MLP matrix multiply. So when you multiply these two matrices, you get a result that's looking like L, F by M. M here is equal to 4, the number of model parallel GPUs I'm using. and every GPU computes its own local matrix multiply. So what have you achieved? You've reduced the memory pressure from the weights. You've also reduced the memory pressure from the activations now, because the intermediate activations is divided by 4. Plus, you've made everything go faster because the number of flops you expend for this is also divided by 4. Okay. What about the second matrix multiply? So remember that you had this result. This moves through a nonlinear activation, and then you multiply it with a matrix that's looking like a taller matrix. So once again, you split that weight matrix up into the 4 GPUs. So every GPU gets an F by 4 shard. And this is the result from the previous layer. But now your inner dimension F is now sharded across the different GPUs. So every GPU is only computing a partial sum. And hence, you're going to need a communication sink, which is once again an all reduce. And once you're done with this, you're actually done model parallelizing the MLP layer. This is called tensor parallelism, and this is used very commonly in large language models. Once again, we want to make sure that your backward pass is also taken care of. So that is kind of implicit, but just to show it to you explicitly, if your forward pass looks like y equals xw, so you had x, your w was split into different GPUs, your backward pass is always going to look like the conjugate operation. So if you had the weight matrix here, you're going to be transposing that matrix. So if your inner dimension was not sharded, then in the backward pass, it will be sharded, and hence you would need an all reduce in the backward pass. This is exactly the same as in data parallelism. Typically, if your forward pass has no sinks and you sharded something, your backward pass will be transposing your activations or your weights, and hence you would need the conjugate sink, which is an all reduce. And the reverse is also true. If your backward pass is doing nothing because your inner dimension is not sharded, then your forward pass most likely needs an all reduce communication call. Another good news is that if you've done parallelizing your matrix multiply, your self-attention is also automatically parallelized, because they're pretty much the same matrix multiply. So you have an input tensor, another weight matrix. It's of a different size because you have different number of heads and you have queries, keys, and values. But once again, the idea is the same. You split that matrix up into multiple GPUs. You do your forward pass, inner dimension not sharded, so you're good to go. Your attention operation for tensor parallel is really nice because once you split it up and you reshape it, all your heads are now on different GPUs. So this entire operation becomes embarrassingly parallel. So you as a user has to do nothing. You just have to make sure that every GPU holds a local number of heads. And then when you kind of aggregate the results, it's another matrix multiply with now the inner dimension sharded, and hence you have computed a partial sum, and then you do an all reduce. Okay. That's actually all it takes to tensor parallelize your transformer. Any questions there? So that was very similar to data parallelism, except it was different dimensions, and you're just splitting your problem up with more GPUs. And once again, the rule of thumb is if you have split such that your inner dimension is sharded, you need to do a communication sink. You have to always make sure you take care of the backward pass. I have noticed that if you use like AI coding assistants today, they will forget about the backward pass and give you wrong answers. So you have to be a little careful about that. And typically you do model parallelism in tandem with data parallelism. So you want to use more and more GPUs to shard more and more dimensions of your multidimensional tensor. Okay. Any questions? Yeah. That's right. Yeah. Yeah, exactly. That makes tensor parallel a very expensive operation. And I'll come to how do you think about the performance of that in the later slides, but that's exactly right. Yeah. Very portable. Okay, I'm not too sure about things like Samba Nova and like these very specific accelerators, but if you're using like AMD GPUs or Intel GPUs, they all have their associated communication libraries. Like sort of nickel, it's called Rickle, and so on, and Sickle for Intel. And from the PyTorch side, you would just say backend equals nickel, backend equals nickel, and then it will use the underlying software it needs to do the communication. So very portable, and I think every single major company has spent a lot of effort in making sure the user side doesn't change too much. Yeah. Okay. So coding this model parallel aspect is a little bit more involved. We typically will use some tool to do it automatically for you, but I just want to show you what those tools do underneath the hood. It's just, once again, it's mostly like 3-4 lines of code, but it's kind of important for you to understand how it's done in PyTorch. So you will get a chance to look at this code in the hands-on. But the basic idea is if you want to additionally tensor parallelize your model, normally you would have called, let's say in your MLP layer, you will define FC1, which stands for fully connected layer number 1, as nn.linear with some input features and hidden features. Input features is E, hidden features is F for us. That is now going to be replaced by a function called to distributed matmul. That's a user-defined call that I'm going to show you how to build. Okay. What that distributed matmul will do is it's going to implement that the tensor parallel matrix multiply from scratch. It's fairly straightforward. When you define your weights and bias, which is the weight matrix, I didn't talk about the bias, but it's dealt with the same way. You just kind of add another vector to it. You would define your learnable parameters as a local matrix. So initially, if I had an E cross F matrix, then every GPU will now define this matrix to be E cross F divided by number of tensor parallel GPUs. So that's what this dimension underscore local means. And depending on which layer you are, it's either E cross F by 4 or F by 4 cross E. And all you have to do is tell PyTorch that this is going to be your local, the local size of your weight matrix. And then your forward function, and this is the full implementation, is going to do a local matrix multiply. You're just going to call PyTorch's linear, which is going to do the matrix multiply for you. But you can take care of that communications on your own from the PyTorch side itself. So here, we're going to need 2 routines for that. One that does all reduce in the forward pass and one that does it in the backward pass. The reason why we're using 2 routines is because there's 2 different matrix multiplies in the MLP operation, but you could do it separately as well if you want. So once again, routine 1 is, remember the first MLP matrix multiply doesn't do anything in the forward pass, but it does a backward pass sync. And the second matrix multiply in the MLP does an all reduce in the forward pass, but in the backward pass, it doesn't do anything. Okay, so it's always going to look like this. You're going to always have conjugate operations everywhere. So routine 1 needs to be a routine that you implement that says it's going to be an identity operation. So just pass the input through to the output, and you're going to call torch.distributed.all reduce in the backward pass, and routine 2 will do exactly the reverse. So that's what these 2 routines are going to do. It's called, I just called it copy to parallel region and reduce some parallel region. And PyTorch gives you all the tools that you need to actually implement this without actually going down the software stack. So PyTorch allows you to inherit from torch.autograd.function, which tells PyTorch exactly what to do in the forward pass and the backward pass. So in this case, in the forward pass, you tell PyTorch that you want to do an all reduce. In the backward pass, you tell PyTorch don't do anything. Just take your gradient output and pass it through. Okay. The symbolic stuff is usually not necessary. It's only when you're porting models between different software frameworks. So you can ignore it if you want. Similarly, the second routine is going to be in the forward pass, I'm going to do nothing. There's an input. I'm going to return that input. And in the backward pass, I'm going to take the gradients and I'm going to all reduce it. So once you've implemented this, when you go back to this forward function, it automatically will take care of the sinks where it'll either pass the input through, compute a local matrix multiply and reduce the output, or in the backward pass, it'll also deal with the gradients by either passing the gradients through or reducing the gradients. In most industry tools for parallelization, if you go underneath, let's say, a tensor parallel layer, there will be a function that looks like this, which is class and inherits from torch.autograd function, which is going to implement exactly the same thing. Okay. And once you have implemented the MLP's matrix multiply, your attention operation, the entire model parallel attention is just this code. For your QKV and your projection, these are matrix multipliers again. Instead of calling nn.linear, you would just do a function called your distributed matrix multiply. Okay, so just one line changes. And you want to make sure that because you're reshaping in the heads dimension, that your total number of heads locally is the total number of heads divided by the number of GPUs that you have. So if you're using, let's say, 8 GPUs and you had 16 heads, then every GPU would just get 2 heads. And you just want to let PyTorch know that that's going to be a dimension of your number of heads. Everything else in your code remains exactly the same. The distributed matrix multiply will take care of defining smaller weight matrices and doing all the communication syncs. And the attention operation is embarrassingly parallel in the heads dimension, so there's nothing for you to do. Okay, so this is like the PyTorch side of things. So with just a few lines of code, you can now do data parallelism and tensor parallelism in PyTorch without relying on any external library. But if you want like even better performance, sometimes it's good to rely on external libraries because libraries from NVIDIA look for opportunities for overlapping even the tensor parallel communication. It's a little bit dicey. Sometimes you get good performance, sometimes you don't, but in any case, it will really do better than your own framework. So that might be something to think about if you're really training really big models. But if you go underneath the hood of calling the model parallel layers, they will just be implementing pretty much the same thing by implementing the all reduce and conjugate operations using an autograd function. Okay, any questions on the code aspects? And in the hands-on, we will see these within the GitHub repository so that it's clear to you how things work in the grand scheme of things. Yeah. Oh, yes. No, it works. You can just wrap it up with torch.utils.checkpoint and it'll take care of recomputing things for you. What do you mean by recompile? Yeah. There is some little bit of bookkeeping that you have to do, but yeah, typically you want to have like a trade-off between checkpointing and model parallelism. Some layers are better for just checkpointing. Sometimes it's just better to do model parallelism. In most cases, especially for transformers, instead of checkpointing, if you just model parallelize it, you will get a much bigger performance advantage just in terms of raw speed, which is what's important to you if you're training a model for like a couple of weeks. Yeah. Okay, it kind of depends on what you like. Some people like more button kind of frameworks. In that case, it can be useful. And some people like a little bit more control over what they're coding up. In general, whether it's PyTorch, Lightning, or anything else, it completely depends on what you want to do. If you're training a language model on language data, but just very specific to your domain, maybe, then you want to consider using tools more than writing things from scratch. But in some other domains, let's say like weather forecasting, or let's say you're doing medical imaging, your data is not looking like sentences. You probably have different performance considerations. So at the very least, you want to at least understand what you're going to do underneath and see if you can use a tool. And if you can't, you want to write things from scratch using PyTorch. PyTorch Lightning will not give you this flexibility. So I recommend that you use PyTorch. And like I was saying before, PyTorch is actually coming up with model parallel utilities now, where you don't have to do this. You can just call into PyTorch's framework. It's called dtensor, capital D tensor. That's specifically for defining distributed tensors. And PyTorch, just like DDP, will take care of all the communication syncs underneath the hood for you. It's still experimental, so this keeps changing every year. They started it like a year and a half back. It still doesn't reach the performance of like frontier model code from like NVIDIA or something. But I think it's a good bet to expect that PyTorch will reach that. They're usually very fast in development, and maybe a year from now, we will just recommend you completely move to PyTorch. Okay. So the last part of model parallelization is also very important. It's all about orchestration. Just because you knew how to do a distributed matrix multipliers doesn't mean you will just magically get the performance. You need to make sure that you actually split up your entire workload nicely into data parallel GPUs and to model parallel GPUs. Once again, it's pretty simple, but sometimes people get this wrong and hence don't see the performance that they get. You will always want to orchestrate your GPUs assuming a hyperrectangle of processes. What does that mean? It means that, let's say it's in 2 dimensions, you always logically assume that you have a 2D array of GPUs. So for example, if you're doing model parallelism, let's say tensor parallelism and data parallelism, you're going to assume logically that you have an M cross D array of GPUs, where M is your number of model parallel GPUs, and D is the number of data parallel GPUs. So in this example, let's say I'm doing two-way data parallelism. That means I'm going to split my batch early twice, and I'm doing four-way model parallelism. So in each local batch, the model is so big that I'm going to use 4 additional GPUs to just split my weights up. In total, I have 4 times 2 GPUs. I have 8 GPUs in total. So that's what you see here. So there's GPU 0 to GPU 7. For data parallelism, you're going to split your data into 2 partitions. So these are your data parallel groups. Each data parallel group is 4 GPUs now. So in this case, this first group will get the first batch dimension, the first batch shard. The second group will get the second batch shard. And within this, you're going to use 4 additional GPUs just to split your weights up. So when you're doing all your communication syncs, your data parallel all reduces, which is your weight gradient all reduce, will only happen across these 2 groups, whereas your model parallel all reduces will happen within this sub-model parallel group. So, and this can be extended arbitrarily. So let's say I had pipeline parallelism, things like context parallelism. So language models are trained with 4-dimensional parallelism. So they use data, tensor, pipeline, and context. So technically they have M1 plus M2 plus M3 cross D GPUs. That's the total number of GPUs that they use. And it's the same strategy. So in this case, I have 16 GPUs in total. I'm going to do two-way data parallelism, and then I'm going to do pipelining across 2 ways, and then I'm going to do tensor parallel within 4 GPUs. So, you can keep extending that. How do you do that in PyTorch? You use torch.distributed again. You just tell torch.distributed which GPUs you want in your data parallel and which GPUs you want in your model parallel. In the hands-on section, I will show you exactly how to do that, how to code that up. It's once again just a few lines of code, and then you can actually visualize where all your GPUs are going. Very important, and that relates to one of the questions, you want to optimize your layout based on the communication density. So once again, for data parallelism, there's a lot of overlap opportunities for communication. So you're not really that dependent on the bandwidth. So you want to make sure your data parallel goes across the slowest bandwidth. So which means you want to put data parallel groups across multiple nodes, which have slower bandwidths. In systems like Perlmutter, you have NVLink between GPUs, which is much faster bandwidth using the NVLink technology from NVIDIA. Other machines have other kinds of technologies for the same thing. And parallelization strategies like tensor parallelism, you want to put within a single node because they're on the critical path. You're doing a lot more all reduces for every single layer. So you place them within NVLink domains so that that communication costs effectively comes down. Okay, so a general rule of thumb is for tensor parallelism, you want to place them on the fastest bandwidth. And then for data parallelism, you put them on slower bandwidth. If you're using context parallelism, you would, and I'll talk about that a little later, you also want to put it in high bandwidth domains, but if you don't have it, then you want to keep them as close as possible together. Okay. Are there any questions on the orchestration side? And I think that part will be more clear in the hands-on because you actually get to play around with assigning GPUs to different domains. Okay. Yes. Mm-hmm. So you're asking if it's possible to do something more custom with the GPU layout? Oh, make it automatic? Okay. I think it gets, the more you do complicated workflows like this, like online training with the simulation, um, probably the more control you want, or like optimizing the layout, because simulation stacks have different costs. Um, if they're also big matrix multiplies, you probably could do something automatic. But if there's something else, then you might have to think about load balancing and rearranging your workload to maximally take advantage of the GPUs. It's much more challenging. I think it's pretty much an open research area now, what to do if I have a big neural network and a big simulation that's getting trained in tandem. These are like workflow questions. It's pretty open-ended. But as of now, PyTorch won't recommend that you automatically do something. Like you could, maybe there are like open source tools out there which will probably tell you, but there are things like SmartSim, which is from HPE, which are like allocation managers. They will kind of decide where your resources need to go. But again, these are like experimental tools. So yeah, if you're doing expensive things, you probably should be profiling, looking at performance carefully, and not doing something automatic, because it's expensive and it's a risky business. Okay. I think I have like 10 minutes. Like, yeah, okay. This last part is going to go super quick. Honestly, I think most people already do this out of the box. So this might not be anything new, but there are some quick optimization tips that you want to make sure you're using so that you're getting the most out of a single GPU. So before you even think about going to multiple GPUs, in general, you want to make sure that that expensive hardware that you're using is being utilized to a good extent. There's a bunch of settings in the PyTorch data loader that you can just switch on, and then you would just get more performance in general. Most users automatically keep this on, but if you're not, it's something to consider. The PyTorch documentation, which is linked here, actually tells you exactly what to do. Some of these parameters are for the data loader, the num workers parameter. You want to set that greater than 0. It does default to 0, but you want to make it some larger number so that the PyTorch data loader can use multiple processes to actually feed data into the GPU. So what happens if you use a default parameter, which is 0, your CPU ends up bottlenecking your entire data pipeline, and your GPU is just waiting for data all the time. And that can really kill you if you're training your models at scale. Usually, we recommend that you try something like 2, 4, or 8 for num workers. It's a little bit of some tuning that you have to do, and you should typically see that bottleneck go away. You also want to use pin memory equals true in this data loader to ensure that the hosted device data transfer is pretty quick. So pin memory is a type of CPU memory, which is kind of locked, which is really good for transferring data between your CPU and GPU. If you didn't keep that to true, then there's like additional data copies that need to be done, and that can sometimes take a slow amount of time. Persistent workers is another parameter that's kept to false, but you maybe want to consider setting it to true for long training runs. What this means is that the data loader will just reuse all of the multiple processes that you had, the multiple workers that you had from the first bullet point across multiple epochs or multiple training iterations, so that you don't spend time regenerating those processes. Sometimes you might have to do custom things to collate your batch. In this example that we're going to be looking at, there's nothing custom. It's all like nicely sized images. But you can think about cases like in language models, maybe your sequence length is different between different samples, and you might want to pad it a little bit. If you want to do any of these kind of custom operations, then you can use custom batch samplers and collate functions. When you're loading data from your file system, uh, you should load them in big contiguous chunks as much as possible. And for some of the more complicated things, which ends up happening when you're scaling your models to large sizes, your hosted device transfers can still be slow. Sometimes it'll take a little bit of time before you're, even if you do num workers greater than 0 to get them onto the GPU. You have some opportunities here to put that hosted device transfer on a different CUDA stream. So you can kind of fetch the next data parallelly to some compute, your forward and backward pass, so that all of that cost is hidden. The good news is if you're actually doing some of these more complicated things, at least for NVIDIA machines, we recommend you use NVIDIA DALI, which will automatically do all this for you. So if you build your data loader with DALI, it's fast. It hides all this device transfers and does it in the background, basically. It doesn't have any Python overheads because it's all written in C++ underneath the hood. And if your workflow has a lot of augmentations that you're doing to large tensors, which typically happens in like vision data sets, then DALI will do that for you on the GPU, which is faster than doing it on a CPU. So if your workflow has any of those components, then you can consider using a more advanced data loader. I think there's some good documentations from the PyTorch side as well to use DALI. But anyway, I've linked, I put a link there so that there's more information available to you. Okay. In general, for large-scale training, people use mixed precision training, and that takes advantage of the tensor cores from the GPUs, and that's primarily for accelerated compute. So mixed precision means you combine your FP32 with lower precision, like FP16 or BF16, wherever possible. So your compute-bound operations can get massive speedups, and your memory-bound operations also gets up to like 2x speedups because you're only storing half the number of bytes. Not all operations can be done in FP16, specifically things like reductions or summing operations or like exponentials, sinusoids, cosines need to be done in higher precision. But again, in PyTorch, if you use the automatic mixed precision package, underneath the hood, PyTorch will figure out which operations can be safely done in FP16, which ones need to be done in FP32. From the coding perspective, what that means is in green is the coding changes that you would make to your training workflow. You would just wrap your model in this torch.cuda.amp.autocast, and that'll figure out which operations need to be done in FP16, and some operations like the loss computation itself will usually be done in FP32 because it does a lot of summations. For FP16 in specific, you need the scalar object, which is a torch.cuda.amp.grad scalar, because the dynamic range for FP16 is pretty small. It can't represent very large numbers and very small numbers. And many times when you're training, your gradient becomes too small to represent, and it kind of underflows. So what the scalar will do is it'll scale your loss function by some scalar value when it's computing the gradients, so there's no underflow. It will step 3 optimizer with the scaled, with the unscaled gradients. And if it needs to change the scale dynamically, and this happens if it detects any like nans or infs in your gradients, it will update the scale as well. So this is, again, taken care of automatically. If you use BF16, which is another data type from Google, actually, let me go back. So BF16 is very similar to FP16, but it doesn't have that much precision. So it's far less accurate, but it has a lot more exponents. So its dynamic range is pretty big. And so it's less likely to go into this underflow, overflow issue. So you can actually get rid of all of the scale, and you just have to wrap your model up in the autocast. Okay, this was the same thing. AMP will take care of everything for you, and you should see a pretty big speed up just by using AMP on a single GPU. Especially for transformer models, these are so compute bound because of large matrix multiplies. I highly recommend that you use AMP wherever possible, unless for some reason your workflow needs very high precision. Last thing is to do kernel fusion using just-in-time or JIT compilation. The basic idea here is that every operation that you apply on the PyTorch side will call a CUDA kernel. If your operation is really large, like the matrix multipliers, you're probably okay. There's no latency in calling that CUDA kernel underneath the hood. But for smaller operations, and especially pointwise operations, you might want to consider fusing them into a single kernel. So why is that important? Here's a very simple example. If I have a function and all it's doing is squaring the input and multiplying it by 2, If we actually look at how much time it takes to run underneath the hood, it's pretty quick, sure, because it's a small operation, but the actual operation on the GPU is extremely tiny. And the reason why it takes so much time is because it launches two kernels, one to do the square operation and one to multiply with the scalar. And you can imagine that this gets worse and worse with more pointwise operations. So let's imagine that you had this algebraic function that you want to compute. That's going to launch 7 different kernels. The computation itself is tiny, but it takes a long time to do this computation because it's, the CPU side is just launching the kernels, and there's a lot of time spent there. In PyTorch, all you have to do is decorate that function using torch.compile, or I think you use like JIT also, and it will fuse all of those operations into a single CUDA kernel. And you can see that if you actually do that, all of those gaps from the previous slide disappear, and then your function actually runs in almost negligible time. Even for torch.compile, it's pretty simple. You can either be very aggressive and just wrap your model in torch.compile. So you can do model equals torch.compile of your model. And then PyTorch will automatically figure out which operations it can fuse into larger operations. It can also write like Triton kernels underneath the hood if it needs to make things go faster. In terms of actually getting performance at scale, I would say it's a little bit of an art. Sometimes it works, sometimes it doesn't. So it's good to like, yeah, check out. Oh yeah. Well, I've had mixed experiences with torch.compile. There's actually a really nice link. I'm going to put on Slack, which talks about like the art of using torch.compile, what kind of where it might break and where it might not. I will say when you're doing model parallelism, it can break in very weird ways. All these autograd functions that you define sometimes are not compiled properly. What we did in the code is we just disabled torch. You can actually disable. So let's say you wrap the full model up in torch.compile, you can disable specific regions. What is recommended is if you're running transformer models, it's likely that your model is already pretty optimized. Attentions call into optimized kernels, matrix multipliers call into optimized kernels. So you might want to think of doing things a little bit more manually, like just decorating the loss function with torch.compile and any sort of metrics that you're computing with torch.compile, and leave the model itself. In the hands-on, we kind of wrapped everything up just to show you how it works. Yeah. Yeah. No, I think this automatically, if you do this and you profile it, it'll be a Triton kernel. And yeah, and then you can, there's actually an option that you can, I can Slack you the exact option, and then you can actually see what it generated. And it's just some Triton code. Yeah. Yeah. And I don't know if you're familiar with like Insight profiling. Yeah, if you just look through in that blue region there, if you do torch.compile, it'll actually say Triton something something with some, yeah. Yeah. Okay, good. So I guess just some resources for performance and parallelization. So once again, the goal here was to kind of provide you with some intuition on how things work, but there's a ton of resources online there. If you understood how these distributed matrix multipliers work, then all of this is pretty much within your reach. The PyTorch performance tuning guide is a long tutorial. It includes everything that I've talked about today. I mean, it doesn't have the model parallelism, but that's like a separate section. But it gives you some good practices that you should be looking at as a user. And I highly recommend that you take a look at the tuning guide. PyTorch DDP is, again, your one-stop resource to understand distributed data parallel, what it actually does underneath the hood. If you're working on slow machines, how should you implement DDP? If you're working on other kinds of machine, how should you do it? There's a lot of example codes, again, highly recommended. Model parallelism is a little bit more complicated. Today, I think Megatron, LM, and DeepSpeed are still the most performant libraries out there. it's very difficult for you to beat the performance of these libraries. So Megatron is from NVIDIA and DeepSpeed is from Microsoft. But once again, if you go within the Megatron repository and just look at the tensor parallel code, it's going to look very similar to what you've already seen here. So if you're using model parallelism at scale, I recommend you check out these libraries as well. PhysicsNeMo is another library from NVIDIA that's very specific to scientific problems like high resolution forecasting or physics-informed neural networks and neural operators and things like that. There's model parallelism within PhysicsNeMo as well. Again, it looks very similar to what I've described. So if your domain kind of aligns to that, it's another package that can be pretty useful. If you're using large language models, Hugging Face is excellent. Hugging Face Accelerate implements all of this model parallelism within the transformer, specifically designed for language modeling. So that could be your main source of resource if you're doing that kind of training. Although I am not 100% sure about this, but I think they might be continuing support only for PyTorch. So that's something to be looking out for and not the other workflows. Okay, but there's a lot more, but I think these are some good starting points for you to dig deeper into performance and parallelization in general. Okay, so that ends the lecture portions. Are there any more questions? And in the hands-on, we'll do this entire thing again, but just with the actual code, and we'll do it on NERSC. There's a pretty sizable reservation that we requested, like 3,000 GPUs. Hopefully it works, and hopefully you get a chance to train some big models. Okay. Oh, yes. Okay, if you have time, okay, all the materials is in that GitHub repository. And you would once again access the system via Jupyter, or if you're a traditionalist, you can use SSH into your terminal. I usually prefer the latter, but we recommend you use Jupyter for today because you want to look at some logs of training loss and visualizations of the results.